Hi everyone, as Kadi said, my name is Etienne Bernard, and I will talk about machine learning in the Wolfram language. And before that, I would like to talk a bit about what the Wolfram language is. So it all started in 1988 with software Mathematica, and I'm actually using this software right now, so you can see this notebook interface with cells. Right now I'm in a presentation mode. And at first, Mathematica was mainly software to do math, for example, solving equations or visualizing functions. But nowadays, it's much more than that. There's been a lot of development. And that's why in 2014, we decided to call the language that is inside Mathematica the Wolfram language. So that's really what Wolfram language is. And to give you an overview of the characteristics of this language, I think the main one is that it's a high-level language, in a sense that you can do a lot with a little amount of code. Another interesting thing is that it's a symbolic language. It means that everything in the language is actually a symbolic expression. So in order to see that, so here is an example of an expression, which is just a formula. And you can see that it's symbols that are wrapping other symbols that are wrapping other symbols. And it's hard to believe at first, but actually all the language is based on that. And here is another way to see the expression, and not just formula. Like you can even do, let's say, user interface using a symbolic expression, and it's a surprising, powerful paradigm. Another aspect is that it's a language that is mostly functional, so you can still do procedural language, like in C, for example, but usually the way we developed in the Wolfram language is in a functional way, so doing functions, sub-functions, that are good names, and that don't have side effects, which make it easier to debug. Importantly, this language has many instructions, so to speak, that we call functions. So there's about 6,000 of them, and they span most domain, scientific domain and industrial domain. You can have an idea here of in the web documentation of the domain it covers. And all these functions are carefully documented. So if I don't know, image restoration, for example, let's look at image address. There's good documentation, and okay, that's another part. Another important part is that you can have direct access to data, and this is a byproduct of Wolfram Alpha. So and also access this data with natural language interface, which is interesting. For example, if I do control equal, I can start typing natural language, and I can ask, for example, stock price of Apple from, I don't know, 2012 to 2015, and I press enter, and okay, so it understood the request and it translated it in the Wolfram language, and then I can do, for example, let's say, actually, let's just evaluate that, and we'll see time series, and if I want to visualize that, I could do a date list plot. And here you go, you can visualize the data. Okay, and finally, something that is quite recent, and actually that's at this time that we decided to call it the Wolfram language, is that it has some deployment mechanism. So basically, any code you do in the Wolfram language, you can make an API out of that will be hosted on our servers, and through this API, you can embed this code in any project you have. So yeah, that's a very important part. So let me show you one example of more real-life code, a bit more complex than what you would see in documentation. So here, by the way, I use a code cell. So here it's kind of having a text file environment. So it's called blur faces. It takes an image as input, and the goal will be to find the face in this image, blur them, and output so this image with a blurred face. So there's one part that is called find faces. So this is one of these 6,000 built-in functions. And if I do F1, I can access the documentation and see how it works. And then there's a function that I created myself that is called create mask, that is basically taking the bounding box where the face are, the image, and kind of creating the region that has to be blurred. And then this region is blurred and the image is composed to give the result. So actually, let's try it. Let's try it with an image of myself. So I'm doing current image from the webcam. Hopefully, okay, that's me. And I can now blur my face. And okay, my face is blurred. And just for fun, I can do a dynamic around it. And now you will see in real time my face, okay, getting blurred. Okay, so the program seems to work. Now let's deploy it so that everyone can use it, or you can embed it in your project. So I'm going to create a form function where I tell that the input is the image, then I will blur this image, and the output will be an image in the format PNG. Okay, so there's this form. I could actually try it locally, but I'm going to directly deploy it to our cloud, setting the permission public so that everyone can access that. And now this just created a website that should perform this program. So to test it, let's take an image that has a lot of face, like the Solvay conference. Okay, this one is good. And here I could give the image many ways, but let's just drag and drop it and submit. And hopefully it blurs all the images. Okay, so that's the way you can deploy a program. And this was deployed in a form, but you can also deploy it in an API. And for that, you just need to change form by API function. Okay. All right, so this was all for the Wolfram language. Now let's talk about machine learning. So I want to talk quickly about what is machine learning. So basically, we can say that it's when a computer learns a model from data, and a model can be a program, can be seen as a program with tunable parameters, and the learning can be seen as tuning these parameters to fit the data, or more often to perform the task that you want the program to perform. And so this model can be simple, so just curve fitting, it's already machine learning, or it can be more complex, such as a neural network, to do image classification. And I'm sure you will see some example of that in my talk and in the next talk. So the typical tasks that machine learning is good at is tasks such as classifying images, sound, text, or the type of data, or predicting a numerical variable as function of other variable. Text translation, machine learning is very good at that. Predicting the future of a time series, or detecting where anomalies are in some data. Clustering data as well is a typical machine learning task. Or even, let's look further. If you want your robot to learn how to walk, machine learning can be a way to go. And all these tasks are usually clustered in 3 learning paradigms. The first one, and that's the most common, it's a supervised learning paradigm. It's each time you want to learn to predict an output as function of input, and the data is giving it to you as input-output pairs. Okay, so you just learn a function from example of this function being evaluated in a way. And so this will be tackled with supervised learning because dataset is given as a list of as images that are tagged according to their class. This also would be tackled with supervised learning. This as well, so you see you have an output given an input, and probably your data will be given as a bunch of sentences that are translated in another language. Then there is a bit less common paradigm, but it's more and more used. It's called the unsupervised learning paradigm. This time you don't have input-output, you just have inputs, and you want to learn something about these inputs, for example, or train a model on this input to do some tasks. So data clustering is a classical example. You have a lot of data, you don't have any labels, and you want to cluster the data. Anomaly detection is another example, because often you don't have a data set with a lot of tagged anomalies. You just have a data set of valid example of a normal behavior. And you will use unsupervised learning to learn some statistical regularities in a way from this data set, and use that to figure out where there's something wrong going on. And finally, there's a reinforcement learning paradigm, which is each time you have an agent that is active on environments that gets feedback from this environment, and this agent tries to behave as good as possible in this environment, for example, to get some reward. So for example, for a robot to learn how to walk, this would use the reinforcement learning paradigm. This is not much used yet in the industry, but there's a lot of research, and it's very likely that, let's say, in 5–10 years, it will be a heavily used learning paradigm. So I'm going to talk mostly about, only about supervised learning and unsupervised learning in this talk. Okay, so now in the Wolfram language, what do we have? So one part of our functionalities is an automatic machine learning framework. So these are high-level functions such as classify, predict, that are very easy to use. So they are meant to be used by people that are not expert in machine learning, even that don't know anything about machine learning. Although they can also be used for more advanced purpose, but that's we want to have a very low cost of entry. So they are task-oriented, as you can see. It's not create this model, it's classify, predict, cluster classify, feature extract, and so on. They are automatic in the sense that the algorithm will be chosen automatically, the parameters will be chosen automatically. And another interesting thing is that they can take a wide range of data type, and they will also interpret the type of data automatically. So that's what I will talk in this presentation. And then more recently, we added the neural network framework, which is kind of a lower level way to do machine learning. So this time it's model oriented. You can specify exactly the model that you want. And so here is a simple example, which gives you a high flexibility and also high performance. And you can train this network on GPU and train with large data set that doesn't fit in your memory. And that's what Tushida and Sebastian will tell you about. And finally, there's other class of function we have in our language is function that we trained ourselves using machine learning with our own data. And that's what I will start talking about. So built-in machine learning. So one place where we have built-in machine learning is in classify and predict. So for example, built-in classifiers, if I say classify language, it will load a classifier function that then can be used to identify what the text is in. So Kelly long, it understands it's French. I can also ask how confident this classifier is about the language, and you see that it's pretty confident, but then if I start messing with it by putting some English, you see that it's less confident, and English is appearing. And all right, and I guess if I remove the French one, it will be pretty confident that this time it's an English one. So there's some other built-in classifiers, and you can have a look in documentation. Another built-in function are image identify. So this is something that we did 2 years ago, actually. Train on 10 million of images using deep neural networks. And okay, so the task is to figure out what is the main object in an image. Then there's functions about natural language processing. In the field of natural language processing, text structure is a function that will try to find a grammatical parsing of sentences. And text cases is a function that will try to extract things from a text. For example, we can say, let's grab the Wikipedia page of the moon, and let's extract all the quantities in this page. And that's what it outputs. Or I can ask, let's extract all the nouns, and let's take the 10 most frequent nouns. And apparently, the most frequent are surface, moon, water with 29 occurrence, and spacecraft with 20 occurrence. Okay, actually, I forgot to mention, because you will hear it in the next talk, but there's another type of built-in machine learning is a built-in neural network. So you can use net model to download various neural network, and for now there's not that many of them, but we're working hard to have many neural networks at your disposal. But this I'm sure you will hear in the other talks. Okay, so now let's look at the function that we allow users to train their own machine learning model. So for that, let's get a data set of images. So I'm going to use web image search to grab 20 images per character of Guardians of the Galaxy, and so okay, so I should have about 80 images. So it's using in the back end Bing and Google Image, and these are the requests to Bing and Google Image. And from that, I'm just going to shuffle all this data set. Okay, hopefully this is working. Seems to have an issue. So most of my examples are based on the data set, so I really need to get this. Okay, let me think of a solution here. Oh, this seems to work here. That's interesting. What I will do is just to put these images on my hard drive. Okay, and I'm going to get them. So I'm transferring from Mathematica to the other. So here are the images, and I'm going to shuffle all of them. So here is just a bunch of images that have no information about the request that has been made to obtain them. And let's start to play around with these images a little bit. So first, what we can do is visualizing these images in a two-dimensional feature space. So there's a new function in 11.1 that is called FeatureSpacePlot. And what it does is that it converts images to numerical vectors using a deep neural network, by the way. And these numerical vectors are rich in the semantic of the image. And then this numerical vector, the dimension of these numerical vectors are reduced to 2 in order for us to visualize this data set. And you can see that even if it doesn't have label information, you still have, for example, the Groot character seems to be located in this area. It seems like the raccoon is around here. So of course it's not perfect. I think there's a bit of characters that are different, probably because they have the same background that are next to each other. But at least you can see that the Wolfram language has already understands a little bit about these images, even without any labels. And so just to show you how this feature extraction works in practice, you can also use the feature extraction function on these images, and this will output a feature extractor function. And this feature extractor, you can use it on new data. So let's take, I don't know, this image, and so you see it extracted a numerical vector. And this feature extraction not only works for images, it works for many types of data. For example, here I have examples that are a mix of text, of color, and a date. And this will manage to extract numerical vectors from this example that are probably useful for subsequent applications. And one of these applications might be to do a search system. So there's 80 images. So I'm going to separate these images into a search data set of 70 images and query images to 10 query images. And now I'm using the function FeatureNearest on this search data set, so on these images. And what it does is doing feature extraction, and it will allow to figure out what is the nearest example in this search data set in this feature space. And hopefully, because the feature space has a lot of semantic embedded in it, it should allow to have nearest image that makes sense. So let's say, I don't know, let's say I take first one, hopefully we'll get a raccoon. Okay, so that seems to be the nearest image actually, and also opening his mouth. I don't know if that was a lucky shot or not, but I can take the Groot guy and hopefully, oh, actually it seems to be the same image but cut, so that makes total sense. Okay, that's how you can do a semantic search system. That's one application. Okay, now let's move on to a more classic example that you will have more chance to encounter in practice, which is the task of classification. So before, this was all unsupervised learning application that I was showing. This is a supervised learning application. So we're going to tag all the image according to their search query. So let me show you the 5 first examples. So you see now this image is tagged as Star-Lord, this one is tagged as Gamora, and so on. And there's 80 image. I'm going to create a training set of 60 image and a test set of 20 image. And then I'm using the function classify on these 60 tagged images. And classify will also extract features, but also figure out what are the features that are important and not important to perform this classification. So it's a bit more advanced than just doing distance in the feature space. And as you've seen, I didn't have to put any extra arguments. So it found out what is relevant, the good algorithm and the good parameters by itself. And now this classifier function, I can use it. So let's look at some examples. So if I look at this guy here, okay, it predicts that it's Rocket Raccoon, great. And I can ask, like in the example of the built-in classifier, what are the probabilities, for example? And it's pretty confident it's Rocket Raccoon here. Let's take a harder one. Maybe this one is harder. And here it predicts that it's Star-Lord, but this time only 84%. So in order to have a better idea of how good this classifier is, you can use classifier measurements, which the first function is a classifier, the second function is a test set, and this will help us to assess how good the classifier is on this test set. So it's very important that the test set contain images that were not in the training set in order to have a good estimate, in order to be sure that the classifier is not cheating by just remembering by heart the training images. And so you have a classifier measurement object, and now you can query from this object what is accuracy. So apparently there's 85% of accuracy on this test set. You can ask to visualize a confusion matrix. So you see that in the diagonal, it's the correct classification, and the off-diagonal terms are the misclassification. So interestingly, there's 3 Star-Lord that have been misclassified as Gamora. So let's look at them, actually. So I can ask for example, and Star-Lord classified as Gamora. I think that's it. Okay, there are the 3 Star-Lord classified as Gamora. I don't know why, but this might be a useful way to figure out, let's see the Gamora that have been correctly classified. So to figure out if there's a problem in your data set or not. So as you see here, there's a little amount of data, just 60 examples, and yet it got a pretty decent accuracy, 85%. And that is mainly due to the automation, but mainly due to the feature extractor. Okay, and then you can ask things such as what are the worst classified example in terms of probability, so actually they are the 3 misclassified, or what are the best classified examples. So apparently this example, the classifier really believes that was very right about the answer in terms of probability. Okay, so let me show you another example of classification, because that's really the most common task, but this time on text data. So here we have a bunch of snippets of text that are actually Facebook messages that have been tagged according to their topic. So let's get a random one. Hopefully there's no offending things in it. I apologize in advance. Okay, en route to LAX, blah, 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 and it has been tagged as transport. And there's a bunch of them. Wasting the weather away, being indoors, it's about weather. Okay, so let me get 100,000 of them. and run classify on it. And this again try to figure out what is the best algorithm, what are the best parameters. It will output a classifier function. And then instead of using classifier measurement, this time I'm just going to play with a dynamic interface where I can type some text, and the classifier will tell me what it thinks in terms of probabilities are the topics. So here we go, and so I can say, I don't know, I like, so far it thinks personal mood, okay, I speak about myself, carrot, oh, food and drinks, but only 20%. And if I do soup, okay, carrot soup, 75% of chance that it's about food and drink, still a chance that it's about personal mood, and maybe a little bit about fitness as well. I guess, yeah, fitness people like carrot soup maybe. Okay, so that was a final example for classify, and I'm going to give you one final example of this high-level machine learning function on the task of predicting numerical values. So before we're predicting a class, right? This is a class like weather, food and drinks, personal mood, and this time is about predicting a numerical value. So let's grab a data set from resource data. By the way, that's a new way to get data set, and there's many, many of them that we added. And let's look at the description of these columns. So you see you have a bunch of features. And the last one is the median value of houses in the neighborhood. So what we'll try to do is to predict this median value as function as all the other characteristics of this neighborhood. Okay, so to do that, let's create a training set with 400 data, test set, I think it's about 200 data. And I will use the function predict this time because the output is a numerical value, as I was saying, a real value, a continuous value. And this time, the input is a data set. And so I just indicate the column that I want to predict. And by the way, I also use an option, performance goal, that basically tells the computer, I have time, so do the best you can. Okay, so now we have our predictor, so we could use it directly on your example, but let's measure directly the quality of the predictor by creating a predictor measurements object using the predictor and test data. And now we can do things such as give me a comparison plot, which is a bit the equivalent of the confusion matrix but for predict. So each example, it means that this test example had this predicted value and this actual value. So if the prediction was perfect, all the text example will line on the median line. And if the predictor was very bad, then there will be data points everywhere. So you see that it's not perfect, but it's not, but it's useful. It learns something. And now I can ask things such as, give me the example that are in this box. So we'll do it like this. And here are the 4 examples that are in that box. Or I can say, give me the standard deviation of the region, or the standard deviation, and then what is the uncertainty on the standard deviation. That is pretty high here because we have a small test set. And there's many other things you can ask, so you can see in the documentation. Okay, so that will be all for the high-level machine learning functions. And there's some other functions I didn't talk about that you can look in documentation, such as cluster classify to do clustering, find formula to find simple model that fits your data, or active classification, which is useful when you have a data set that doesn't have labels, but when you have a sort of oracle that can label the data that you wish to be labeled. That's a kind of another paradigm. Actually, it's kind of encompassed in the reinforcement learning paradigm.